let's consider the following pair of hard set equalities. I first encountered these in grad school, so take that as a warning on the level of difficulty. On the other hand, these are great fun for trying to wrap your head around. Now, start with x, it's going to be a set. We'll have a family of subsets of x, call it a sub k, where k is in the natural numbers. So we'll have a sub 1, a sub 2, a sub 3, and so on. We'll have these two set constructions. So if I take the union as I goes from 1 to infinity, the intersection as j goes from I to infinity of a sub j, the claim is that that's the same as the set of all elements in x. They're in all but finitely many of the a sub k's. For our second one, okay, we're going to take the intersection as I goes from 1 to infinity of the unions j going from I to infinity of a sub j. The claim is this is the same as the set of all elements in x that are in infinitely many of the a sub k's. Now, before we do any proofs, we have to wrap our heads around what each of these items actually means. Okay, the important one is, what's the difference between this and this? We'll do that by considering a few examples. Now, for our first example, I'll consider a sub odd equal to 0, 1, a sub even equal to 2, 3. So if we consider the number line and mark off our points, a sub 1 is going to be 0, 1, a sub 2 is 2, 3, and then these are just going to alternate back and forth. Now, if we're considering how often a given point occurs in these sets, I could just consider, for instance, the vertical line that goes through 0. So that's just going to be a line, and we're going to mark off dots for each a sub k that 0 shows up in. Now, what does all but finitely many mean? So that's saying there's going to be some finite set where we don't really worry about whether our point is in the set of indices or not, but we're going to hit some index where our point shows up in those subsets all the way down. So we're looking for this solid block of points. For infinitely many, okay, this condition's not as stringent. So the idea here is, as we consider this line going all the way down, okay, we look to see if a point shows up, and then as we go down, that point has to keep recurring. So the idea is that we're not going to hit a final point where past that point, the point of interest never shows up again. Now, if we apply these two qualitative definitions to our sets, what happens? Well, if you consider any vertical line through these points, we're never going to have that solid block. So for the points that are all but finitely many of the a sub k's, we're just going to have the empty set. For the points that occur in infinitely many of our sets, okay, well, for instance, 0, okay, it's just going to alternate. It's in, it's out, it's in, it's out. So that'll be in infinitely many. Okay, it's always going to recur no matter how far down we look. So that means we'll have all of our points in here. So for 2, we'll have 0, 1, 2, and 3. That's everything. For another example, let's consider a sub odd equal to 0, 1, a sub even equal to 1, 2. Same idea as before. The sets are going to alternate, except now 1 is going to be in every set. For all but finitely many, we look to see which point has a block occurring beneath it. That only occurs for the point 1, right from the start. So for all but finitely many, we have the set 1. For infinitely many, we're looking for the points that recur over and over again. And that'll be each of these. So since we're alternating, they're going to show up, okay, every other one. So for 2, we get 0, 1, 2. For a final example, let's consider a sub k equal to 0 union with, then we're going to take all integers starting at k and then going out. For the picture, what do we have? 0 is going to be in every set. Then as we increase k, we're just going to drop off one integer at a time. So we note here, Okay, the only way we can have a solid block to get all but finitely many is if we consider 0. Likewise, for infinitely many, okay, we'll have 0. But if we check any other integer, okay, positive, then we know that there's going to be some point where it stops recurring. So that means for both 1 and 2, we have the point 0. Now, that takes care of the right-hand side. Okay. To consider the left-hand side, we're just going to do the proofs. Now, I want to show that two sets are equal. We need to show the double inclusions. So let's start with the first one, which is straightforward. Okay, we're going to have our union intersection of the a sub j's is equal to all x that are in all but finitely many a sub k's. So for the first inclusion, I'm just going to assume that we have x in this set here. If this x is in this union, that means it's going to be in at least one of these intersections. Okay, so let's just say for some I, we have x in, okay, the intersection that starts at I. Now, if x is in this intersection, that means it's going to have to be in every set that's in the intersection. So that means for all j greater than or equal to I, we have x in a sub j. Now, that's going to mean all but finitely many of the a sub k's. Okay, once you pick this I, x is going to be in all of these sets past it. We don't know about the first I minus 1, but we're sure about the rest. So that gives us what we want for this direction. Now, in the other direction, okay, if I have x in all but finitely many of the a sub k's, okay, well that's going to mean there's going to be some fixed I, where if we look at a sub j past that, our x is going to be in there. So that means, okay, we're going to have x in these a sub j's, so x is going to be in the intersection of these a sub j's, okay, and that's what we're writing here. Now, if it's in one of these, okay, it's not going to hurt to throw in all the rest of the sets that look like these with a union. Okay, as long as it's in one, we can say this. So that gives us our other direction. That means these are equal. For number 2, things aren't so straightforward. It's recommended that you try to figure it out yourself before continuing. We note, I want to consider x that appear in infinitely many of the a sub k's. Okay, so remember, infinite just means not finite, and we can wrap our head around finite. So what we want to do here, we want to use two proofs by contradiction to get our double inclusions. So the way we'll start, okay, it's going to be proof by contradiction. For the first inclusion, we're going to assume that x is in the left-hand side, and we're going to get our conclusion assuming that x is in only finitely many of the a sub k's. Now, that means there's going to exist some I such that x is not in a sub j for all j greater than or equal to I. So that's what it would mean to be in only finitely many of the a sub k's. Because of this, that means x is not going to be in the union, j going from I to infinity, of the a sub j's. So that means x is not going to be in the intersection of all of these unions. So it's going to show our first inclusion. So that says if x is in here, then x is in infinitely many of the a sub k's. For the other direction, okay, we're going to assume that x is in infinitely many of the a sub k's. Okay, so we're going in the other direction. And we're going to assume that x is not in, okay, the intersection of the unions of the a sub j's. So not in here. Now, if we're not in here, that's going to mean, okay, we're going to have some I such that we're not in one of these sets here. Okay, we're going to blow the intersection. So that means x is not in, okay, some union, j going from I to infinity, a sub j. So this means x is not going to be in each of these a sub j's under consideration. Now, that's just saying, okay, if you take a look at what we're doing here, okay, x is not going to be in the a sub j's for the j's that start at I and go out. So that means we're in at most finitely many of the a sub j's, okay, the ones that go from 1 to I minus 1. So we're in only finitely many of these, and that's going to be a contradiction to our assumption that x is in infinitely many. Now, that means we have our other inclusion, so that means our two sets are equal.